they're getting there. But these ones are online. So, so I think most of you know me from last semester, right? So my area is also game theory, but especially kind of mechanism design part within the intelligent agents topics. So what is mechanism design? So far what Maria has been covering is the behavior. So given a game, how will agents or how should agents behave within that game, right? That's what we're doing in game theory. So if we have a multi-agent system and we want to say something about this system, whether it works or not, we can apply game theory, right? That's one of the tools we have. The other tools could be simulations, for example. Right? But game theory is one of the main tools within this area that's used to analyze these kind of multi-agent systems and to predict what kind of behavior will emerge, essentially. And Nash equilibrium is a good predictor of rational behavior, at least. Making certain assumptions, so it's not always perfect. So, but in multi-agent systems, actually, we are creating often the system ourselves. So if you're thinking of stock markets, for example, we could create a new market, right? So if we can design this new market for a multi-agent system, how should we go on designing the system? Okay. We want the system to have certain desirable properties, that agents are incentivized to behave in a certain way within this system. Okay. So this is essentially, we are going to design the system in order to direct the agent behavior in a certain way, even though the agents themselves are what we say self-interested, right? So they are about, the agents maximize their own utility. By the way, self-interest is not the same as selfish. Okay? So self-interest simply means they pursue their own goals, and they could be in conflict with other agents' goals, right? If they're doing good things for the environment is your goal, that could be your goal, but maybe someone else's goal is different. So given that each agent has its own goals, how can we design a system in such a way that actually on a whole we get some interesting desirable properties? Okay? So this is a key thing for multi-agent systems where we look at self-interested, so kind of non-cooperative kind of agent systems. Okay? And this is where mechanism design essentially comes in. So we're designing the game. It's not anymore given a certain game, this is how the agent will behave, but how can we design the game in such a way that the agent will behave as we want them to behave? Yeah. So I'll go through introduction, then look at various option types, which we covered last semester very briefly, and then continue on to looking at more advanced kind of mechanisms. So mechanism design is often called reverse game theory because of that. So it's not that we, given a game, we analyze the game, no, we're creating the game. Okay? Given that players are playing in equilibrium, but how should we design the game such that in equilibrium the agent behave as we want them to behave? So an example is the prisoner's dilemma, right? So the prisoner's dilemma has an equilibrium which is not desirable because both agents defect, which leads to an equilibrium which is suboptimal, right? If the agents were able to collaborate with each other, they could reach an equilibrium where both of them would benefit. Okay? But because of the way the game is structured, in equilibrium, the agents will go to a defect kind of equilibrium. So can we change the game such that the equilibrium is different? Okay? So how do we design a game such that certain objectives are met in equilibrium? This is what mechanism design is about. So there's two kind of main applications here, or two kind of areas, they're not really applications. One of them is about elections. This is a method to, say, coordinate agents. So suppose we want to make a decision, so the multi-agent system needs to make a decision, a joint decision on some aspect. For example, what doesn't matter so much. So we could use, for example, a voting protocol, like we use a democracy, right? So we need to decide whether to build a bridge or not, for example, and we're all involved in this kind of decision. Then we can use, say, democratic voting. That works very well. So we can also use these techniques in multi-agent systems. And Maria will talk about that after Easter. So what I'll be talking about is mainly marketplaces. So suppose we have certain resources we want to allocate. So these could be computational resources, they could be energy in a smart grid kind of setting, or they could be, and we'll look at the application of advertising, so advertising slots, right? So we have this kind of scarce resources, and we want to design a mechanism so that they get allocated in a desirable way. So what is a desirable way? So what is good in some allocations and what is bad in other allocations? Well, a good thing is if the outcome is efficient. So a lot of agents might want these resources, but we want to allocate the resources to those who actually need them the most. Okay? So how do we go about that, given that every agent is self-interested? So if we simply ask an agent, how much do you need these resources? They say, obviously they're going to lie, right? So I need these resources a lot. So then all the agents will lie, and then we can't make a good decision based on these lies. So we have to incentivize the behavior of the agents. So something like, maybe how can we incentivize them to be truthful about how much they need these resources? Okay? Another call could be, we might say a seller is maximizing, is selling these resources. Maybe we want to, instead of efficiency, maybe we're more interested in maximizing the profit. And sometimes the seller is like a third party who's not supposed to make profit, maybe the government. So the government wants to, have an efficient outcome and is not interested in making profit. So maybe we actually want to minimize the seller's profit and make sure that a lot of the money goes back to the cynical smile there. Goes back to the people. So that could be, let's say, non-profit organization that have that kind of goal, right? So we'll focus on these kind of marketplaces. So we've already encountered kind of mechanisms which we can use to allocate resources, right? And these are called auctions. Okay? So we saw those in last semester, and I hope you still remember some of those lectures, right? So you did very well in the exam, by the way. So I think you will remember some of it at least. So we posed the question of saying, okay, there's these 4 types of auctions, and I'm not going to go into detail anymore. I assume you know what they are. So we had the English auction, which is the standard auction, and we had the Dutch auction, which is, we said, was equivalent to the first price sealed bid auction. And then we had this victory auction, the second price sealed bid auction, where the winner pays the second highest bid. Right? And we saw that it was strategically equivalent to the English auction. Right? So they had this auction had this dominant strategy to be truthful, And we asked this question, so which one is better? Right? And what was the answer? So to analyze this, there's various ways of analyzing it before I get to the answer, right? So we use game theory to analyze this, right? So now you know a bit more about game theory. So I'll go through it a little bit again. What did we assume? So we assumed that each bidder has a private valuation, so willingness to pay, theta I for an item. The utility is this theta I minus any payments if the bidder, whoever wins the item, okay, and utility 0 otherwise, assuming the payment is 0 for people who are not a winner. So theta I is essentially the price at which you be indifferent between winning and losing. Okay? So that's quite important to remember what this theta I means. Okay? And we assume that the utility does not depend on others people's value for the item. So in this kind of setting, we said that these are private valuations, so private valuation setting. And we assumed as well that each bidder has a belief about the private valuation of other players. Even the auctioneer might have this kind of idea about, so it might have a probability distribution about the valuation of other bidders, but it does not know, no one knows the valuations of other bidders. You only really know your willingness to pay. So if the auctioneer asks, so what are you willing to pay for this item? It does not know, the other bidders do not know, so we have to elicit this information. Okay? But we might have this kind of beliefs or probability distribution about what other people's value might be. Each bidder maximizes spec utility, and we assume that bidders cannot collude. So this is, we did this last semester, and under those conditions, we derived equilibria for those options. And I didn't go too much detail then. And again, I won't go into too much detail now because actually I want to focus on these kind of truthful options rather than these not truthful. So we found that, for example, in the first price sealed bid auction and also in the Dutch auction, because they are strategically equivalent, we had this strategy where we have a Bayes-Nash equilibrium, and I believe Maria briefly touched on Bayes-Nash. So in a Nash equilibrium, you have perfect information about the utility functions of other people, right? So in Prison's dilemma, you know exactly if this strategy is played and the other player plays this strategy, I know exactly what the utility is of the other players. There's no incomplete information. The only incomplete information, essentially, is about what the agents play. But in equilibrium, I know what they play, okay? But here, in equilibrium, we don't know what the types of other players are. Okay, so we have this, this type that we don't know. So we don't know utility function, essentially, of the other agents, because that depends on their type, their theta I. Okay? So we have to, there's this concept, Bayes-Nash equilibrium, which can be used in a setting where we don't know the utility function of others, but we have this idea of the distribution of other players. So we have a Bayesian game, becomes a Bayesian game. Okay? And we had this strategy, equilibrium strategy for, if we assume this F, this distribution, is a uniform distribution, the simplest distribution you can think of, then the equilibrium strategy is where everyone is a function of someone's type, and it looked like this. Okay? So this is the equilibrium strategy in the first price sealed bid auction, given that my type is theta I, and I know that other people's types are uniformly distributed. Okay? So this kind of equilibrium relied on the fact that, first of all, the players play rationally. So everyone plays rationally, and everyone knows that other people will also play rationally. And moreover, that we have this information, F, of the distribution of other players. Okay? But not only that, there's an assumption that I know this distribution, but I know that other people know that I know this distribution, etc., etc. So there's this common knowledge assumption of the distribution information. Okay? So the details are not so important, but it's important to understand what those assumptions are that game theory makes in this kind of analysis. Now, then we looked at the victory and English option, and I hope that you remember that in these kind of options we have a dominant strategy, where the dominant strategy is to bid truthfully, right? But does anyone need a reminder of that? So, no, otherwise, okay. So an equivalent statement is the option is truthful or strategy proof or incentive compatible in dominant strategy. So we have a theorem that the victory option is strategy proof, and we have the properties here. It is optimal to bid truthfully regardless of what other agents are doing. Now, the interesting thing here is that we did not, well, first of all, it's not Bayes-Nash equilibrium, it's a dominant strategy equilibrium. So therefore, whereas in the previous option, we had an equilibrium, but it's very kind of unstable equilibrium, right? So if other people are acting not rationally, it's in my interest to change my behavior as well. So if I know that, you know, in a poker game, you know, when you're playing poker, it depends on which opponent you're playing against, right? If you know that you're playing against an experienced opponent, you're going to behave different than if you know that you're playing against a novice, right? Against a novice, you can exploit certain things, so you can apply certain strategies to exploit them. Whereas with a, you know, with an expert, with a pro, those strategies don't work. So in these games as well, in the Bayes-Nash equilibrium, if you're playing against a rational opponent, you should behave differently than if you know that your opponent is not rational. However, in this game, the victory option, that doesn't matter. Even if the opponent is not rational, right? Even if they behave really strangely, they bid infinite or something like that, if other people are bidding very strangely, it's still in your best interest to play the dominant strategy, to bid truthfully. Okay? So this kind of option does not rely on the fact that other people are rational. And that's very important when we want to apply these things in real settings. Okay? The other thing that it doesn't assume is this common knowledge assumption. We're not using any information about the distribution of other bidders here. We don't have to reason about them. The game is much simpler in a sense, right? So the reasoning is much simpler, but also the assumption of common knowledge is not present when we look for the equilibrium of this game. Okay? So that's why it's important to understand a little bit why Bayes-Nash equilibrium requires this assumption of common knowledge. So you have to know the distribution, and everyone has to know the distribution, and everyone has the same knowledge of this distribution. Otherwise, you can't derive a Bayesian equilibrium, because you have to reason about how other people will behave, and you can only know that if you know what they know about the distribution. Right? So it's a complex kind of reasoning. Here, the reasoning is really easy. You don't have to reason about what other people are doing. Okay? So that's the key here for why this option might be, in some sense, better. But then we found, and that's again, we briefly touched on that last semester, there's this revenue equivalence theorem, right? Which says that in equilibrium, essentially, all the 4 options that we've discussed come to the same outcome, exactly the same outcome, and even the revenue is the same as well. Right? Do you remember that? No? Not many nods? No? Okay. So what the revenue equivalence theorem said, suppose the valuations for the single items are drawn from a continuous distribution over a certain domain, it's not really important, and all dates are expected, utility maximizers. Then, any 2 options where, in equilibrium, the item is always allocated to the bidder who values it the most, and then there's a technical assumption here, then it will always lead to the same expected revenue for the auctioneer. So why is this? Well, so in the first price auction, you win. Whoever wins pays their bid, right? In the second price auction, whoever wins pays the bid below them, right? The second highest bid, right? So if everything is equal, obviously in the second price auction you pay less than in the first price auction. Right? That pushes people to bid more in the second price auction than they would in the first price auction. Right? So your payment is, you know that you have to pay your own bid in the first price auction, so therefore essentially you're going to reduce the bid that you're going to bid. So in equilibrium, you're going to bid less in the first price auction than in the second price auction. And therefore, in equilibrium, it all turns out, all cancels out, and the revenue for the auctioneer, so the amount of payment that the auctioneer gets, turns out to be the same. So it's a mathematical trick. Okay? So, but it's very important that we're talking about equilibrium behavior here. So, and this equilibrium, as we saw, relies on a number of assumptions. So, this common knowledge assumption, the rationality assumption, and also here, in this particular revenue equivalence, assumes symmetric information. So, not only do I know about this distribution, but everyone has the same knowledge exactly about this distribution information. Okay? And risk with no bidders. So, when we just look at this revenue equivalence theorem, it looks like, hang on, why do we really care about designing different auction mechanisms? Because it doesn't really matter. All the auction mechanisms, result in the same outcome. So why do we really care? Now, so why do we do mechanism design? Because you think, well, we can do first price auction, we can do second price auction, we can do any type of auction, and in fact the revenue equivalence theorem says it doesn't matter. Well, it does matter, and so there's this thing called the Wilson doctrine. So it's about the practicality of game theory. So when does game theory become practical? So I'll just read this. So game theory has a great advantage in explicitly analyzing the consequences of trading rules that presumably are really common knowledge. It is deficient to the extent it assumes other features to be common knowledge. Okay, so it's reasonable to assume that the trading rules, so if you're saying we're running now first price auction, that people can understand those trading rules. The trading rules themselves are common knowledge. But what Wilson's saying, it is sufficient to the extent it assumes other features to be common knowledge, such as one's player's probability assessment about another's preferences or information. So it's reasonable to assume people understand the rules of the game. It's not reasonable to assume that they have common knowledge about other people's preference distribution. Okay? So it's not a reasonable assumption to make. And he says, I foresee the progress of game theory as depending on successive reductions in the base common knowledge assumptions required to conduct useful analysis of practical problems. Okay? So only by repeated weakening of common knowledge assumptions will the theory approximate reality. Okay? So this is a harsh criticism of game theory, and especially of Bayes' Nash equilibrium. Okay? So it's a philosophical argument, right? But it's really practical as well. So it says really, okay, game theory makes all these assumptions. Can we start to relax some of these assumptions, or we should maybe focus our attention where these assumptions are not, do not necessarily, are not required in a sense. Okay. So when we then compare the first price option and the second price option, even though they are equivalent in equilibrium, we can see that in terms of the Wilson doctrine, the second price option does give a certain advantage. So in addition to requiring few assumptions, advantages, as I already said, so players can make decisions without requiring any distribution information. There is very low cognitive load, since players do not need to reason about the strategy of others when making decisions. Because the only thing they have to do is say, okay, it's truthful, right? So bidding truthfully is a dominant strategy. I don't have to think much about what other people are doing. And the optimal strategy remains optimal even if other agents are rational, etc. So these are the kind of advantages that we say, okay, let's design a mechanism where we have a very simple reasoning process for the agents. So the agents don't have to go into this complex speculative behavior. Okay. So the question then is, and this we'll go back to this principle. So there's a revelation, there's something called the revelation principle, and it asks. So we see that the first price option does not have a dominant strategy, right? The second price option does have a dominant strategy. But this is a very simple game, right? We're allocating one resource. You know, we could think of other situations like voting, right, where we want to get consensus on some sort of decisions, and we want to elicit people's preferences to understand what the best decision is. So can we always elicit these preferences truthfully, and is there always a dominant strategy to do that? Well, no. The answer is no. So for example, when we have interdependent valuations, so my utility depends on what other people value something. So we have this oil drilling example we saw last semester. Then we cannot always define a dominant strategy equilibrium, but we can find a weaker, the Bayes-Nash equilibrium. But we can always find to transform a game where the equilibrium is truthful, even if it's a Bayes-Nash one. At least the equilibrium is a truthful one. Okay, and we'll come back to that and see why this is. So what do I mean? So suppose we have a game where we ask people for their preferences. Okay, we ask the agent for the preferences, and we're going to make a decision based on these preferences. And the agent might have an incentive to misreport these preferences. Okay? Now we can always create another game, okay, where the agents are truthful about the preferences, and the outcome of both games is the same. Okay? But the second game is easier, because the agents are just, the strategy of the agent is much simpler, and we rely often on fewer assumptions. Okay? So we'll come back to this in a bit. So this revelation principle is really, really important at the crucial of the crux of the mechanism design, essentially. Okay? So this is kind of a long philosophical argument for game theory. So what are we doing now? Where am I going with this? Okay? So the options that we did last semester, those 4 types of options, were really simple options. They only looked at selling maybe one item, right? So you're selling one item, and how do you do that? I sold these, they weren't Mars bars, but the sweets last night, right? So in the real life, there's often much more complex situations where we're not just allocating one item, but it's much a complex combination of items. So what we'll do is we'll extend what the second prize option, the principles of the second prize option, to more general settings. Right? This is the advanced class, so we'll be doing advanced game theory or advanced mechanism design as well. So there's this class of mechanisms, or sometimes it's some people call it a single mechanism, but it's the Vickrey-Clark-Groves mechanisms, which can be used. These are kind of generalizations of the Vickrey option. So that will be this week. And the next week, I'll talk about a specific application, which is sponsor search and display advertising, and where these kind of options are used and how we can use them. If I have more time, I'll look at other applications as well. We'll see how we go. Okay, so this was just a kind of introduction, essentially, to why it's important to look at kind of mechanism design. And now I'll go into a little bit more detail. So let's start with a little bit more complex problem. Okay. So suppose you're a student and you're looking for a house to rent, and you need some items for your flat, and there's a fridge, a dishwasher, like a nice luxury flat, and a washing machine, right? Okay. Now, you're interested. Most students are interested in the bundle, okay? But so you don't just want one item, but you want all three, okay? Or a combination of them, okay? So we can describe, say, the preferences. So suppose there's two players who are competing for these resources. Okay? Agent 1 has a preference for the fridge and for the washing machine, or it's just the fridge will give him a value of 100. Okay? Just having the washing machine gives a value of 60, and just having just the dishwasher and just the washing machine actually doesn't want just the washing machine, because otherwise it doesn't match well with the color scheme of the other items, something like that. Okay, so he's not interested in this, but he's interested in maybe a bundle, right? So maybe A and B together. Or maybe he already has actually a washing machine. Okay, so A and B together, he has a value of 180. A and C, maybe 80, and B and C, 40. And then having all the bundle together is a willingness to pay of 160. Okay, so these are just the combinations that it's like, and the preferences for these combinations. Now, on the other hand, we have another player who's not interested in any of the single items, but just interested in these two bundles. Well, this bundle here, where we get the dishwasher and the washing machine, or the bundle where get all three together. Okay. Now, if we have a designer, someone who looks at these preferences and says, okay, based on these preferences, who should get what? Yes?
Player 1 should get A, and player 2 should get B and C.
Okay, and why?
That maximizes the sum of the utilities for both players.
Yeah, exactly, right? That could be a desirable outcome, right? We want to make everyone as happy as we can. Okay? Right? So we want to maximize the sum of utilities of everyone in the system, for example. Yeah? So yes, we should allocate prefer A to player 1 and the other two items to player 2. Okay, that could be a desirable outcome. The problem here is whoever is designing the mechanism, the system designer, does not know these preferences. They are hidden. Only the players themselves know. Okay? So, so what happens if the system designer simply asks, okay, tell me your preferences and I'll do the allocation. Right? So obviously, this player says, oh yeah, A and B are worth to me 1 million. Right? And you know, maybe player 2 is naive and is truthful and says, okay, these are my preferences. Player A knows its games, and the system designer saying, oh, okay, then I'll give A and B to player 1, and player 2 gets nothing. Okay, because they don't want a single item. So you can easily see that a naive mechanism that simply asks for people to reveal their preferences truthfully does not work in this case. It's very easy to manipulate, right? If we don't have some sort of payment or some sort of other incentives to be truthful. Okay. So this so this goal that we have, right? We say we want to maximize the sum of utilities of everyone. Is a goal that we say we're maximizing the social welfare. Okay? The social welfare. There's the welfare of everyone combined. Yeah. And we can formalize this a bit more. So if we have a set of agents and we have a set of outcomes, right? So what are outcomes? Well, these are all the possible combinations of allocations. Okay. So there's lots of different outcomes. So how many outcomes are there in this set? How many possible different outcomes allocations can we have? Go back to your combinatorics mathematics. Year 1, if you're doing the MN. Okay, so we can allocate any item to any of the players, right? So how many combinations or possible allocations are there? What's the task? Think about it. Any ideas? Any suggestions? Yeah?
It's just a guess, but the number of players to the power of items. 8 in this case.
8?
No.
I think it's more actually.
15.
15? How do you get to that?
I don't know how to express, but for 2 players, if you give them each 1 item, you got 8 options. And if you give 2 items for each player, you got 6. And if you give 3 items for 1 player, you're gonna get 1 win. So totally it should be 15.
Not quite. Nice try. Anyone else?
Is it 2 to the power 7? 7 combinations?
No, not as much. No, not as much. That's quite high. Somewhere between. Yeah.
26.
Hmm?
26.
26. I think it's 20. Let me see. It's 3. So it's 2 to the power. No, 3 to the power 3. So 27. Okay. So how did I work that out? Okay. So how do I work that out? So we have. So each item. So take 1 item. Yeah. So suppose we had 1 item. How many outcomes can you have then?
Are we allowed to give no items?
Yes. Yeah. That's it.
So 2 then.
3.
3.
3, right? So we can give it to player 1, we can give it to player 2, or we can give it to no one. Okay. So if we have 2 items, the second item we can do the same. Okay, player 1, player 2, player 3. So the first item has 3 combinations. The second item we have 3 combinations. So for each possible of the other combinations, 3 times 3. And then the third item, so it's 3 to the power 3. Okay. So lots of combinations, right? So you can see that with lots of items, it becomes quite big. Okay. So and lots of players as well. It becomes quite big. So it doesn't scale very well, but that's not the problem for the moment. Okay. So there's 27 possible outcomes. Okay? And the mechanism designer has to choose one of these outcomes based on the preference. Okay, so let's go back to our formal model. So we have set of outcomes, allocations, so X. So that's all the 27 possible allocations we can have. So one of them is where no one gets anything, right? And then we have the set of all possible types. Okay, so these are all the agents. And then we have what's called a social choice function, which is a mapping from the agent's types to certain outcome. So this is here, the mechanism designer here. Okay? So we've got some sort of, we feed in the types of the agents. Okay? We have a function that does something, and that function computes the outcome. Okay? And then we might have some common knowledge about maybe some other distribution, but we don't care about that at the moment. So examples of that is where we maximize the social welfare. Okay? So where we maximize the utilities of the players. Okay? So the utility of a player or of an outcome can also be described in this way. So this is the value that an individual agent derives from its outcome given a particular type. Okay? So essentially, it's kind of this kind of vector of values here. So this gives the value for each possible outcome, right? So I guess these are outcomes for the individual allocations, right? If they get A, but that, you know, using that we can find that we only care about the individual outcome because there's no interdependencies anyway. So, minor thing. But we could, you know, we could specify for each possible outcome the utility for each of these players based on knowing these values. Okay. So I formalize, that's it, formalizing this value. So this is the value for possible outcome. And this is then a particular social choice function could be, and that's the most common one that's used in the computation systems, is when we maximize the sum of values of the individual agents, right? Like we said, like you suggested, so we are taking the sum of the values, and we want to choose the outcome, so we want to choose an element, small x, from the set of possible outcomes, okay, which maximizes the sum of utilities of them, okay? So if, you know, if this notation kind of looks a little bit scary, the interpretation is quite simple, okay? So we're choosing an outcome that maximizes the sum of utilities. And just to bring it back to our example, the outcome, one of the outcomes is where we allocate object A to player 1 and object B and C to player 2, and that is the only outcome here that maximizes the sum of the utilities. Okay, so one of those 27 possible outcomes is the one in this case that maximizes the sum of utilities of the agents. Okay. So this could be an objective function of the mechanism. Okay? So given the true types of the agents, we want to maximize the social welfare. Okay? So this could be a particular social choice function. Obviously, we have to find a mechanism in which to do this, because at the moment, if we just ask them for their types, they're going to misreport. Okay? So the social choice function does not really say how are we going to incentivize the agents to do this. It just simply says this is our objective function. Okay. So in this case, just using the notation, right? So we have here x is the possible outcomes, right? So we can use like the set notation. So one outcome is where no agent gets the item. Another outcome when agent player 1 gets item A, player 1 gets item B, player 1 gets item C, player 1 gets item AB, etc., etc. We can write all the combinations, 27 of them, as we already said. And the one that maximizes social welfare is where item A goes to player 1 and B, C to player 2. Okay, so this is another way to formalize this what we just said in words. And then when we maximize the sum of utilities, we get to this value. Okay. Just to get you a little bit familiar with this kind of notation, because this is you will need it, okay? And you will use it in the assignment and And it's, well, similar maybe in exam as well. You need to be able to solve these kind of examples. Okay. So we already did this. How many possible? Actually, there should be 200. Okay. So we say that the social welfare is 190. Should be 190. And then the allocation, we call this efficient. So it's so there are different types of efficiency. There's Pareto efficiency, for example, but this is allocatively efficient. Okay? So the allocation is efficient. So we call it the outcome is allocatively efficient. Now, so as I said, so we can think of having this nice ideal of we want to maximize social welfare. Very nice communist idea, perhaps. But how do we achieve this? Right? Given that we are self-interested agents. Okay. So this is about the implementation. So we have the social welfare function that we want to implement. Right? It's not implement as in when you design software or something. So it's implementability. It's a different kind of use in this case. But we want to implement the social choice function. That means in game theoretic terms. So age preferences are unknown to the mechanism. So can we design a game where, in equilibrium, the outcome of the game corresponds to the outcome of the social choice function for any combination of player types? So whatever the player types are, we have this social choice function which says, given the player types, we want to maximize the social choice, the social welfare. Can we find a game where, in equilibrium, this social choice function is achieved, in fact? Okay? It doesn't have to be with games or anything. We can let people play and have a look at their equilibrium and then see whether the allocation corresponds in equilibrium to what we design, the social choice function. Okay? Now, if this game exists, and this game does not always exist, depends on the social choice function, we say that the social choice function is implementable. And the implementable can be in different solution concepts. So the one that we will focus on, and it's the easiest one you might like to know, is in dominant strategies. Okay? So that means that there exists a dominant strategy profile of the agents where, in equilibrium, we're maximizing, for example, social welfare. Okay? So is this clear? Any questions? Because this is a really important point. Okay? This is a crucial point. Okay, so yeah, there's a lot of concepts and it might take you a while to become familiar. So then we come back to this revelation principle, which I described earlier. Okay. So how do we design this game? Right? So there could be millions of games. Right? How do we know which game to choose? Where do we start? Right? How do we design this game? Do we need to consider all possible games to know if such a game exists? Well, there's a specific class of games which are direct mechanisms. So, which is essentially a one-shot game which asks the agents, please give me your preferences, okay? And I will compute the outcome based on your preferences. Okay. And there's an interesting, so the revelation principle, which we stated earlier, actually what it implies is that it says that if there exists a game that implements a social choice function in a certain solution concept, then there always exists a direct mechanism where the agents truthfully reveal their types in equilibrium. Okay. So there's many games. So think of the English auction. Okay? The English auction is not a direct mechanism. The English auction asks, it starts off low, £5, and people start bidding, and then goes on to £6, people start bidding. So that's not a direct mechanism, right? A direct mechanism says, okay, all of you give me your preferences, okay, and I will compute the outcome for you based on your preferences. Okay? So the sealed bid auctions are examples of direct mechanisms, right? In sealed bid auctions, the agents are asked for the preference directly. Whereas in an English auction, it's like an iterative game, it's multiple stages, and people have to, have a kind of continuous sequential equilibrium, etc., etc. So it's not a direct game, even though the outcome, however, is the same, right? So we saw that the outcome, in terms of the outcome where the good, so the person who values the item the most, so the way to maximize social welfare, if you have only one item, right, is to give the good to the person who values it the most, right? Both in the English auction and in the sealed bid auction, that outcome is achieved. So the social choice function is achieved in both games. And this revelation principle says, if we have some sort of indirect game that achieves a certain outcome, there's an equivalent direct game that achieves the same outcome. And the implication of that is that we can actually limit our attention to truthful, direct mechanisms, and we can just forget about all the other games. Because we know that maybe there are other games, and maybe they're more practical than sometimes, but in terms of their theoretical properties, we can just limit ourselves to direct mechanisms, and even truthful ones, right? So we have the first price option, and we saw that there was a truthful equivalent second price option, and they are equivalent in the sense that in both cases, the good goes to the person who valued them the most. Okay? Even though they were shading their bids in the first price option, because everyone shades with a certain percentage, you still, the person who, anyway, the person with the highest value remains to be the person with the highest bid, and so you get also maximize social welfare. So we can use the second price option, which is a truthful option. So we can just focus our attention on these games. So that's the kind of power of the revelation principle. And to prove this, okay, is actually really simple. So and then I'll just give you the intuition really, and then we can have a break. Okay. So what's that revelation? So suppose we have a game here, okay, and we have the agents. That are participating in this game, right? And these agents are playing an equilibrium strategy. Okay? And in equilibrium, there's a certain social choice function f which is satisfied. So in equilibrium, we are actually getting the outcome we want, right? But suppose that, but these are not truthful strategies. Okay? So the game, and maybe this game is not a direct mechanism either. Okay, so this could be a very complicated game, and this could be very complicated strategies. Okay? However, we can replace this game by the bigger game, right? Where we have a player here who submits his true value, true preferences, to the agents, okay? So here we simply include the agents in the game itself, okay? And we can, in that case, the agents will actually play on the player's behalf, but they are actually included in the game. And we call this the mechanism here. So because the agent maximizes our utility, the players have an incentive to maximize, to give their true preferences to the agent. So this bigger game is essentially a truthful game now when it comes to truthful game, right? Because these players are playing equilibrium. So we can always transform the game where in equilibrium the agents are not truthful to a bigger game or different game where the agents, well now these are the agents and they are truthful, right? Because we can always incorporate these agents as part of our game. And that's exactly what the second prize option does, right? Because the second price option is essentially, what it does is the auctioneer actually takes the manipulation into account, right? Because if you would know the other player's preferences, right, you would just bid just above the second highest bidder, right? That's what you would do, right? So if you remember, so suppose you know that, these are the preferences of everyone, and you're playing a first price auction, right? A first price auction. Then you know, then this agent would bid 40 plus epsilon, right? So it would bid 40 plus epsilon, essentially. So by including essentially the strategic manipulation that it could do, by saying, okay, let's set the second price according to what is actually optimal for that bidder, okay, we make actually the auction truthful. So essentially, that's what we're doing. The first price auction is a strategic, one where you have to strategize and shape your game. And we have an equivalent game where you have to report your true preferences, in a sense. Okay? So, this is kind of the intuition. Okay? So of what the revelation principle essentially is about, and how you could kind of easily show that this must always be the case. Okay, so shall we have a small break now? So 10 minutes or so, yeah? Then we'll continue in the 10 past.
What